over some fixed base field K with a symmetric monodal structure was given by tensor product over that base field. And we saw that this is the same as giving an associative algebra, a unidal associative algebra over K. And how did this go? Well, given a functor f, we asked, hey, what do you do on the connected one-dimensional disk? It gave me a vector space that I called A, and the embeddings of disjoint unions of intervals gave me the multiplication. Okay. And then what we did was we noted that disks are just examples of all one-dimensional manifolds that are oriented. And I defined something called the left Kahn extension to be the factorization homology with coefficients in A. Okay. So note that I'm kind of abusing notation. Of course, F is more data than just A, has multiplication, but I'm not going to want to write F all the time. I'm going to write A all the time to connote, hey, we have an algebra lying around. Okay. So we defined this as a left Kahn extension, and I said, don't worry about what the definition is, and it satisfies a property called tensor excision, which I will review later in today's talk. But first, I wanted to make some comments about infinity categorical thought, because we saw it in at least one other talk, and clearly it's going to be useful to think about what infinity categories are like. So let me make some remarks about infinity categories. Okay, so the intuition that I gave yesterday was as follows. So an infinity category, script C, is just a category such that for every pair of objects, say x and y, inside of C, the collection of morphisms is a topological space. And of course, composition if I have a map from y to z and a map from x to y, I can of course compose them. The left-hand side has a direct product topology, the right-hand side has a topology. This is continuous. So this is what one would normally call a topologically enriched category. Okay? And as it turns out, topologically enriched categories are fine models of infinity categories. So whenever you see an infinity category, you can feel free to replace the word infinity category with this data. And there's camera training today at 1:45 in the overflow room. And speakers that intend to use slides, please notify Tim with the nice shirt, as David said. All right. I'm going to erase this. It's very important for infinity categorical thought. But what's more important about infinity categories is not what they are, but when they're equivalent. So an equivalence. So a functor. For my lectures, so I'm going to give you a bunch of things. I'm going to tell you how to think about it. You're going to nod along. And then I'm going to destroy your universe by saying in practice, this isn't exactly all the examples. And you'll see what I mean in just a second. But before I destroy your universe, let me construct your universe. Okay, so a functor from C to D is the usual notion of a functor. It's a functor in the usual sense. So, it sends objects to objects, morphisms to morphisms, and it respects composition in the unit map. But that such that the induced map in morphism spaces, so in the category C, if I have two objects x and y, I can send them to two objects called f of x and f of y in my category D. In my definition of functor in the usual sense, I have a map like this, and I demand that this is continuous. Okay, so that's the place where we're using that we have a topological space structure. And the important part is we say f is an equivalence. If all these induced maps between the home spaces, I'm dropping x and y because I'm lazy as h, induced isomorphisms on the set of connected components of these spaces. So pi naught is my word for connected components of topological space. Pi 1, fundamental groups at all possible base points. Pi 2, so on all homotopy groups, it induces an isomorphism. You should think of this, if you're more familiar with chain complexes, as analogous to the notion of quasi-isomorphism. Of course, a chain map is called a quasi-isomorphism if it induces an isomorphism on all cohomology groups. And this is the exact analog. It's when we want to think of two spaces as equivalent. It's when the only algebraic invariant that we can extract from them are all isomorphic by a continuous. Okay. Should I say more about this? So this is i.e. the weak homotopy equivalence. So this is called the data of a continuous map that induces isomorphism. All these is called the weak homotopy equivalence. I should say that pi naught in general is just a set. So an isomorphism with pi naught is just a bijection. Yeah, Tim.
Well, I think you're going to get to it, but I think so far it's not fully faithful with your functors.
Oh, sorry. This is called, yeah, and if f is essentially surjective, as usual. Thank you. Sorry. I wanted to say the important part, and I forgot the also important part. Anyway. Right, so essentially it's surjective. It's the usual condition on categories. You should hit every single object in the target up to isomorphism. All right, so let me just make a couple of remarks, which remarks that I want to make. Okay. So remark. So in an infinity category, C, we can speak of when objects, or we can speak of equivalences of objects. Okay, so this is not to be confused with the notion of equivalence for infinity categories. Now I'm zooming in on a single infinity category called C. So an equivalence is the data of some morphism from x to y. So this is an element in the space called Cx comma y, such that there exists a map G going the other way, and homotopies from the obvious compositions to the obvious identities. Okay. So if this symbol, homotopy, were replaced with the symbol equality, that would be the usual notion of isomorphism. If I have a map f and g such that their composite is equal to the identity, those are mutually inverse, just like nature sees. But here I'm not demanding that these maps be the identities on the nose, I just demand a homotopy to the identity. And the notion of homotopy makes sense in any topological space. So f composed with g is some point in here. Or f composed with g is some point in the space of endomorphisms from y to y. And so is the identity. And this is a topological space, so I can ask for a path between the two. And that's what I mean by homotopy between two maps in an infinity category. Okay, are you ready for this universe to be destroyed? So that's the intuition. In practice, especially in algebra, these morphism spaces are almost always combinatorially defined spaces. So let me give you an example of this principle that we actually saw yesterday. So as an example, let's say that C happens to be the category of chain complexes over K. And I shouldn't say category, the infinity category of chain complexes. Okay, so this is the infinity category of complexes, and K here is a field. Okay. So we have a set that I'll call the set of chain maps. Sorry. If I have two chain complexes x and y, I can look at the set of chain maps. So these are the usual definition. It's maps that respect the differential on either side. And there was a question asked yesterday, how do I topologize this set? I don't. This is a set of vertices of something combinatorial. So I define this space as the following. It has vertices. So this is what I mean by combinatorially defined. I define it similar to the way you would define a simplicial complex. You just have a bunch of simplices and you attach them all together. And then we have edges given by homotopies. And we have triangles given by homotopies between homotopies. And so on. Okay? For instance, yesterday Pavel talked about the infinity category of CDGAs. Okay? So there, an object in the infinity category of CDGAs is just a chain complex equipped with a commutative multiplication. That's what a CDGA is. And I guess he also imposed that everything be concentrated in non-positive cohomological groups. We know what a map of CDGAs is. It's just a map of chain complexes that respects multiplication. It's just a commutative algebra map. Okay? But when we consider this an infinity category, well, we also know when two maps of algebras are homotopic. I'm not going to give the definition, but you can define it. And that puts an edge between two algebra maps. We can ask for higher homotopy, that puts in the triangles, etc. So in algebra, in practice, the usual set of morphisms that you're used to, it lives there. You don't topologize that set. You just add edges and triangles to that set. That's what almost always happens in practice in algebra. And as a result, somehow, usually when we write down functors between these algebraically defined things, what we need to verify is not the continuity of these maps, but we actually usually verify something combinatorial. Our vertices sent to vertices, our edges sent to edges, our triangles sent to triangles. That's usually what we actually verify in most infinity categorical sets. Final caveat. In my lectures, again, this paradigm, what makes factorization homology difficult? To set up. We've set it up for you, so you're good. But what made it difficult to set up is these two categories manifestly are different kinds of categories from a philosophical perspective. Whether this be vector spaces or chain complexes, this is algebraic. The kinds of morphism spaces that we want to define here are all combinatorial in nature. On the left-hand side, of course, when I said the space of embeddings, everybody nodded along like, yeah, totally, topological space, got it. Now, of course, there's standard ways to get around this, but fundamentally, somehow, the difficulty of coherence that you need to express in factorization homology, for instance, for things like, hey, why should a continuous space of diffeomorphisms act on an algebraic object? That incompatibility is manifested somewhat superficially, but it is still manifested in these two different philosophies of topological space versus combinatorial spaces. I wanted to make that remark. Are there any questions about what I said just now? Let me make just another remark.
So how is this?
Yeah.
How is this related to this other point of view where an infinity category is actually not a category?
Oh,
because
yeah. So I would highly recommend. So if you don't actually have to use models of infinity categories in practice, I would recommend disposing of whatever philosopher told you that, and think of infinity categories literally as categories enriched in topological spaces with this notion of equivalence. In fact, there's a theorem of mathematics that says that whatever notion of infinity category you had in mind is, in a well-defined sense, equivalent to this model. Completely equivalent. No holds barred. So I would very much encourage you to ignore whoever told you that.
I was just worth remarking that there was a period where various models were constructed before people knew that they were on the
Yes.
Kind of historical confusion that people think it's harder.
Right. So for instance, like when I was a grad student, there were many ways to think about this until I discovered a paper of Julie Bergner, which is one of several, but probably the main reference, describing all these models as equivalent. I didn't realize I could sleep at night. But you can, and if I've destroyed another universe somebody created for you, I apologize. But I highly encourage you to think of it this way if you don't need to work with the nitty-gritties. Yeah.
So, since we're talking a little bit about philosophy,
Yeah.
so you're talking about this universe, you're destroying it. So when you said, "Hey, we do things combinatorially," I went, "Woohoo!"
Great, great.
But it sounds like you're from the point of view that there's something like we'd rather live in the topological world. There's something like wrong about that.
No, there's nothing wrong with either perspective. This is a There's nothing wrong with either perspective. It's just that I can imagine that when somebody hears topological space, there really is some like flimsy, floppy topology. And in practice, especially in algebra, I just wanted to assure you that you don't need to do that. You might get worried that, but not all my examples look like that. I promise you, you don't need to worry about it. Yes. But yes, maybe I didn't destroy anything. I just kind of made the universe nicer.
You make me happy. I was like, yeah.
I'm happy to make you a better universe. So let me make another remark about infinity categories. There's some confusion about the word A infinity, and we're never going to use it again, so you can forget it, except for this following remark. So you might hear me say something like, there exists a contractible space of blah. Okay? So you might hear me say something like, there exists a contractible space of multiplications on an A infinity algebra. You heard me say that yesterday. And if you are you, what I want you to think is this a unique blah. Let me say why. What's the definition of contractible? The definition of contractible is that there's a space, space of blah. Contractible means that, so maybe this is the easiest way. Every space is a canonical map to a point. If you want to make a choice, you can also get a map from the point if you like. It doesn't really matter. What does contractible mean? Contractible means all of its homotopy groups vanish. So pi naught is 1, just a single point. Pi 1, pi 2 are all the trivial group. And in particular, these maps are homotopy equivalences. They induce isomorphisms on all the pi i's. Okay? And what's our notion of equivalence for infinity categories? Well, the morphism spaces are equivalent, or two categories are equivalent if they're essentially surjective, and such a map exists between the morphism spaces. So in practice, if you have an infinity category where everything is contractible, then you can replace it actually with a category where the morphism sets are really just sets. And you can go home and check that the category of disks with oriented embedding is precisely such an example. When I have k disjoint one-dimensional disks and I embed them in an oriented way into a target, the space of ways to do that, even though it looks like there's many of them, and there are, that space is contractible. By the same increasing function argument that I mentioned yesterday. So that's another remark that I definitely wanted to make. There's two other things that I wanted to say. I also wanted to clarify this Hawkshill homology business. Okay, so let me exhibit an example of this power of having continuous maps. So another example from yesterday. So the principle that I wanted to illustrate was, so this functor called factorization homology. Let's say now we're in chain complexes. So that, again, K is a field. This is useful because we see in action of the orientation preserving diffeomorphisms of the circle on whatever we associate to the circle. So let me explain how this goes, maybe just step by step. Okay, so because factorization homology is a functor, we have an induced map on morphism spaces. So whenever we have a map from a circle to itself in this category, we have a map in the category of chain complexes. I'm kind of pedantic here, but that's the definition of a functor. I'm provided with such a thing, and this is continuous. Okay. Now let me make the following observation. Because the circle is a Lie group, it certainly acts on itself. It acts on itself by diffeomorphisms. Yesterday I mentioned that the morphisms in this space are all embeddings, smooth embeddings. So C infinity embeddings. And when your manifold is compact and connected, any smooth embedding is in fact a diffeomorphism. So in fact, these orientation preserving embeddings are the exact same thing as orientation preserving diffeomorphisms of the circle. And what I was saying about the circle being a Lie group is, of course, the circle sits inside as a subgroup, acting on itself by multiplication. Now, as it turns out, although we won't need this map happens to be a homotopy equivalence. It actually induces an isomorphism on all the relevant pi I. Okay? And in particular, only on one pi I called pi 1. Okay? So this space, most manifolds, the space of orientation with diffeomorphisms, if you want to study it, you're asked out of luck. In this case, it happens to be simple. Okay. And in particular, if you look at this composition, we have a continuous map from the circle to that chain complex. Now, the circle is connected. Okay? And as such, although every single point in the circle determines a map here, somehow all the maps that you determine are homotopic, regardless of which point on the circle you choose. Are we in agreement there? And so the only interesting thing to look, so we define some map. And of course, that map has to be something homotopic to the identity. So let's look at the induced maps. Let's first pedantically talk about pi naught. So we have a map of connected components. And remember yesterday that the way that I topologized this, or the way that I made this combinatorial, was such that I made the following claim, that the negative cohomology groups of home as a chain complex, okay, were in fact pi k of this space. So pi k of home as a space. Combinatorial space, if you like. I again apologize for my free form. So in particular, I know that the induced map on pi naught is a map on H0 of home. And as I said, because this is connected, it sends the identity of the circle, the identity embedding of the circle to itself, to whatever map it is, it's something homotopic to the identity of this invariant. So that is useless. Somebody gives you a chain complex, having an identity map from it to itself is no additional data. But now I want to look at the induced map on pi 1. So as you know, pi 1 of S1 is Z. You don't need to be a homotopy theorist to know that. And, you know, I don't really need this, but let's choose a generator of home. But as I said, this is something in degree -1 cohomology of the home cochain complex. Okay. And so where is this element 1 sent? I claim that it is sent to something that I'm going to call D de Rham when my algebra A is a commutative algebra. And I remarked yesterday that K needs to be perfect or characteristic 0. Okay. So I would like to unpack what in the world this statement actually means, because I think this is awesome. So there's a couple of things that I wanted to say about this. So one, recall that by excision, the invariant that I assigned to the circle was.
Excuse me, what is the word again where A is
a commutative?
Commutative.
Yeah, it's commutative. So commutative algebras are in particular associative, so I can take their factorization homology for one manifold. So recall that yesterday I claimed that there's this version of excision. It said that whatever I assign to the left-hand horseshoe and whatever I assign to the right-hand horseshoe can be glued together by whatever I assign to their overlap, so long as their overlap is the product with a real line. And this was indeed the product of two disjoint points of the real line. And it was, of course, important that I actually invoked whatever orientation I was inheriting from the circle. So I pedantically wrote real lines with particular orientations. So this was by the excision theorem, so the tensor excision theorem. Okay. And now just plugging in what these are, this is just a copy of the real line. And so factorization homology assigns A to that. Okay. And we reason that this is A tensor A up as an associative algebra. Yeah.
Wait, so in the horseshoe picture where you have the orientations, they're going like in the same direction, the overlap, and then your factorization homology can give them going in opposite directions? Is that?
Right, so on the overlap, so their orientations are compatible with the orientation of the circle. But if you recall the module structure that I put on here, it was by embedding these two intervals like so. And so when you multiply these elements, the multiplication order gets flipped. And that's why this modulo action is by A up and not by A. Okay. And then the one caveat that I said was, this notion of tensoring over something, it has a certain universal property that can be expressed using homotopy theory. And for that, we need to take the derived tensor product here for this theorem to hold true. Okay. So in fact, at this level, the theorem could use the symbol blackboard pull down.
Well, the theorem holds. If you work it with algebra and vect, the theorem would hold without.
That's right. With algebra and vect, the theorem holds without it. But now I'm in chain complexes, so thank you for that.
That's just your notion of tensor product.
Yes, but I just want to be careful. So that notion of tensor product is different from this notion of tensor product.
Sure.
Right? Like, this is tensoring over a different algebra. For things to be homotopically coherent, you always have to take this. And I could have also said the same here. Technically, I should always be doing this if I want an infinity category where quasi-isomorphic things are identified. But that's why I worked over a field. Over a field, everything is free. I don't need to derive. If that's helpful, please keep that in mind. And then I just invoke the theorem. So this is the definition, or one definition, of Hochschild's chains of A. Now, if you come from a walk of life where you've already seen a definition of Hochschild chains, then I recommend that you do the exercise of resolving capital A as an A tensor AF module, and then writing out the Tor, for instance. Or don't even write out the Tor. The Hochschild chains, you'll see, will be a model of this derived tensor product. And then I invoked a theorem called the Htr theorem. Oh, how convenient. When A is a commutative algebra over a perfect field, the Htr theorem actually identifies the homology of this, or the cohomology of this. And let me tell you what it is. So the negative kth cohomology of this is just the kth, the set of degree k Theorem forms, algebraic Theorem forms. So if you like, this is the kth exterior power of omega 1a.
And the left-hand side of that arrow would be pi k of x one. So you have this maps to.
Oh, sorry.
H star and everything.
Let me remove this.
Okay.
And so turns out I can compute the cohomology of this using a theorem called Htr. Okay. So let me draw a picture to make things even more concrete. So in cohomological degree, so zero forms are just functions on spec A, which is just A again. We have the degree 1 differential forms, and then we have, I'll just write omega 2 as though I'm a differential geometer. These are just the two forms. Okay. So when you look at this, something really annoying should strike you. In life, whenever you see somebody draw something like this diagram of vector spaces, you want to put a differential there called the Durand differential. So you want there to be a map like this. Another weird thing is when you think about cohomology, it should be in positive degree, but here, everything is in negative degree. This is the reason I think this is called Hochschild homology and not Hochschild cohomology. If you flip things, these are in positive homological degree. Okay, so there's something very confusing going on. But so the question is there a natural way to recover the differentials, the Durand differentials that you want to draw in a geometric way? Okay, so historically, so I'm going to attribute this to both Baudet and Kahn, maybe? Do you know that double is necessary? So, all right, Baudet, maybe Kahn. So historically, we took this very explicit chain complex called the Hochschild chain complex of A with itself, and combinatorially exhibited a circle action, such that the action induces the Theorem differential that you want to put here. So that's how things went historically, and this was I think this was a pretty groundbreaking combinatorial task. We gave this chain let me not say more, but it was a pretty cool combinatorial thing to realize that there were concrete combinatorics that you could use to model circle actions. Still influenced, yeah.
Can I ask, why would you even expect there to be any circle action?
Yeah, because even before factorization of homology, people understood Hochschild homology to be pictures of algebra elements marked by points on the disk. Like, remember yesterday I drew pictures of two intervals embedded in a circle, and I can move them around, and it's said x1 times x2 was x2 times x1. People understood Hochschild homology to be that kind of construction already. So you could imagine anybody with a geometric, a sense of sight could be like, maybe I can rotate this.
So Hiro, can you say once again what actually is a circle action in that language now?
Yes, in this language, let me not. In this language, let me say.
No, this we understood.
Yeah. So maybe after the talk. Is that fair?
No, but you're claiming that it's a Theorem differential.
Yes, yes.
That's
Oh, wait, sorry. Yeah. Is your question like, can you tell me what the classical model was and what I meant by circle action in the classical model? I haven't told you how to recover the Theorem differential, and I will not tell you because I don't think I even know how.
I'm saying how to recover it.
I'm asserting.
reminding us that
Well, let me tell you.
I mean, basically, you're telling us the circle action is the Theorem differential.
Yes, because so let me
Because that's what you're sort of saying here.
Exactly. So somehow the circle action that was historically exhibited, we are now exhibiting in a one-line proof using factorization homology. Although I haven't proven that this element deserves to be called the Theorem differential, but I'm asserting that it is, and you have to prove that that's not a one-line proof. But it's a one-line proof that you would expect something like the Theorem differential to pop out from the circle action. So again, it's not so much the fact that the circle, acts as a set, it's that it acts continuously, so you can detect its pi 1. That's the power of this homotypical thought, even in this simple example. And later today, hopefully, depending on the time, we'll see mapping class groups acting on certain kinds of categories.
And does it square to 0 because pi 2 of S1 is 0?
Yeah, more or less. Yeah.
So that's actually. So it's not. So d squared is not really 0. Is that right?
It's homotopic to 0. And at the level of homology, it's 0.
If you look at the classical proof of HKR, it's immediate from that proof that whatever the heck combinatorial circle action was there is the Theorem differential. It's evident from the isomorphism between those homology groups and the Theorem complex.
Isomorphism itself. Yeah. Aaron's right. Once you can prove this, the Theorem differential is not. So hopefully this elucidates what I meant by the degree 1 action. It's this element, co-multiple degree minus 1, which of course is a map. It's a degree minus 1 map from this to itself, as depicted there. Okay. I think that's everything that I wanted to say about yesterday. So let me give an exercise. Because it's a school. And of course, you're not tired, right? Sorry, I'm tired too. Okay, exercise. Remark. So we took yesterday 2 examples of categories of a symmetric monadal structure. One was the category of vector spaces in the usual sense. All of its morphism sets were really just sets. We also took the category of the infinity category of chain complexes, where I told you how to make combinatorial spaces and their mapping sets. Okay, so my claim is we can actually take to be any infinity category, to be any symmetric monadal infinity category satisfying the following, such that this monadal structure preserves certain colimits in each variable. So what I mean by each variable, of course, tensor product takes two variables, and each one independently should preserve colimits. What I mean by colimits is just a categorical way of saying how do I glue things together, and which certain kinds of colimits. Turns out that in all the proofs, the only kinds of colimits that you ever need to look at look like things like the bar construction. Such things are called sifted colimits by category theorists and topologists alike. So it just needs to preserve sifted colimits. Okay. And I'm just going to assert that indeed these two categories, these two infinity categories, satisfy this property for the tensor product, as indicated here. And so from now on, whenever I have so from now on, we'll take the symmetric monodal infinity category to be such. So in fact, C needs to have sifted colimits as well. So if you're not comfortable with it, you can just ignore it and things will work through the way that you expect. So here's the exercise. Let's let C be the category of categories with direct product. I want to be careful here. This is a category. I'm going to ignore size issues. So an object here is just a category. And what's a morphism? What's the collection of morphisms between two categories? It's just a collection of functors. Now, this alone would indeed define this as a category, but I'm going to consider it as an infinity category in the following way. Remember, the prescription was algebraically, you usually have a classical collection of morphisms, and then you want to add edges. Okay. And the edges that I'll add is, and say, assert, place. So, cat times can be made an infinity category as follows. It's really not complicated, I promise. Okay. So, home from two categories D to E is going to have as vertices functors. D to E. Anybody want to make a guess as to when there ought to be an edge between two functors? There's two natural guesses. It's a school, so now I'm going to demand your participation. Natural isomorphisms, good. So edges, natural isomorphisms. So these are natural transformations that happen to be isomorphisms on each object. So the data of an edge from f naught to f1 is just a natural transformation, so meaning that the natural map from f0 to x, f1x, happens to be an isomorphism in the category E. Okay? And now somehow the other combinatorics are just quite simple. These are all functors. And let's say that I have three natural isomorphisms, which I'll call eta01, eta12, and eta02. The subscripts indicate the domain and codomain of the natural isomorphisms. And triangles are just commutative diagrams. Commutative triangles of natural isomorphisms. And then k-simplices are just commutative diagrams.
So you're asking the commutative axis to be equal like on the nose, not by via some.
That's an awesome point, yeah. So it's commutative on the nose, and the fault of that is that E is just a category. Right? In E, there's no notion of, hey, I got, what does it mean for this diagram to commute? It means that the natural transformation maps have to agree. There's no notion of homotopy in the category E, it's just a category. So what you're hinting at is a way to think of the category of infinity categories as an infinity category, where the vertices and edges would be as indicated, but now the triangles would be commuting up to homotopy in the category E. Okay, so commutative diagram in the shape of k-simplices. So in fact, even though I call this an infinity category, somehow all the information stops at level 2. Everything else is just equality on the nose. Okay, so what is the exercise? exercise to show if I look at this one-oriented algebras, in this infinity category with symmetric monoidal product given by direct product of categories, this is equivalent to a unitally monoidal. So I'll put unital in parentheses because often it's a monoidal categories. Often when people say monoidal categories, they already mean unital, so I'll put it in parentheses. And so somehow most of this exercise is remembering what a monoidal category is. And here, again, it'll be the idea that associativity isn't an equality, but it only holds up to something will be the important part. That's the point of this exercise. So I promised myself I would take a break after 45 minutes. And I haven't gone to any new material today. Is it okay if I take a break? We don't need to. It's for the sake of the students as well. Oh yeah, question? Oh yeah, I said there's two natural, no pun intended, guesses for edges. Somebody might have said, you know, if you give me two functors, I can construct a natural transformation between them. And the issue there, of course, is that in a space, whenever there's a path, you expect to be able to go backwards. And if my edges were just natural transformations, it wouldn't have a natural inverse natural transformation. So we're throwing out the non-invertible things. And this is another principle of how you often create infinity categories. We'll see examples of categories like this that are, true categorical in that they want, not natural isomorphisms but natural transformations, but we throw out the non-invertible ones. So there are two natural guesses. Only one makes you an actual infinity category where you have a space. All right, so 5-minute break, and I'll see you again at 50. Is that cool? 50 by that clock. All right.
What if you just invert them?
Oh, you know the well, you have a name for the answer. I don't know what that category is. It looks a lot like the.
That could be your other possibility.
Yes, it's true. That's another natural guess. With
Dan, there's a question in inverting them. Yeah, its rule is a colimit type construction. Whenever you propose those, you're in trouble.
I thought this was.
That's so good to hear. This talks about this
Yeah, Z to this. Yeah.
This is the first one that I kind of was vaguely aware of.
Which is some or something.
Oh, well, yeah, for pi
Yes,
one.
that's
It's not possible to think that it's like something slow and sense, not really, which I learned.
If you get like some space,
Oh, no.
then it's going to factor through like the regular equation.
That's right. So in fact, one thing that we did improve is actually if your category is chain, if your target is chain complexes, the map from this, I was going to factor through the. In particular, it'll lose most of it. Of course, pi k's are always smooth.
Yes.
Straight right, and I found the path.
This thing here, you say A,
The good way is to
chain
make
complex,
I see your, yeah.
This is
Oh, okay.
Long and all.
you don't think this is on the chain. This is the.
Live in the time zone you're in.
Chain, like offshore.
Oh, well,
These are the
Which is
chain complex.
because I know here, if you don't take advantage of this,
Exactly.
when it's on, it's only more.
It's just a chain. It's an object.
The standard response when you say, "Oh, beautiful day," it's say,
They'll say what?
"It won't
Won't
last."
last.
Now you would like to reintroduce it from.
Yeah, it's a different view. This view. and that
Yeah.
view. Isn't it?
I can so, yes. And I will ask you later, but I'm not doing your brain.
It's
really well. This camera here
Oh, that's because those. Oh, yeah, we'll complain about them together. Yeah,
Anyway, you will explain.
Yes.
all you do is
Okay, so. Alrighty.
Break is already over.
Yeah, I know, right? Sounds so short.
But some people escaped.
Alright, so use the bell.
Oh, yeah.
Okay. Let's start it. Alright. So while I love one dimension, I'm going to go to higher dimensions. Okay, so today, after that extended review of yesterday, we're going to talk about the higher dimensional case. And I was going to get to TFTs, but I probably won't get to them until tomorrow. Okay, so let's consider the following. Consider symmetric monoidal functors from oriented two disks to the infinity category of chain complexes over a field where the monoidal structure is tensor product. Oh, let me give you another exercise before I do this. I apologize. I keep remembering exercises. This is an awesome exercise. Okay. You might have been annoyed by the orientations. So let's consider just disk 1. So here the objects are not oriented, disjoint unions of R, of course with the empty set as before. And what are the morphisms between two objects x and y? It's just the space of embeddings, smooth embeddings. And again, with no orientation restriction. One of the wonderful things about manifolds is you can demand or not demand structures on them. And the question is, does this change the algebraic structure that pops out on the other side? It's a pretty awesome question to ask. It's not every day that you have a new playground of algebraic structures. So the first thing that I want to note is the first thing that we did when we saw this definition yesterday, which is let's just understand the space of maps from R to itself. Okay, so yesterday, of course, we reasoned that if we have an orientation preserving map, then this implies that this is actually isotopic to the identity of R. Yeah. An increasing function argument. But of course, if we don't demand orientation preserving, we can now have an embedding that reverses orientation. And it's an exercise to prove that this space is actually just consists of essentially those two possibilities. It's a disjoint union of contractible spaces called one reverses orientation, one does not. Okay. So in particular, if I have a function called f, even to say vector spaces, so I'll just denote by C tensor again. In mind, you can think vector spaces are chain complexes. We now have a map. So again, let me call A the vector space or chain complex that I associate to the real line. So let A be that. Now we have two maps. called the identity, and some other map. I can't call it sigma. Maybe I'll call it tau. This is for the orientation reversal. So again, tau is just f applied to the embedding that reverses orientation. Okay. You easily see that if I compose an orientation reversing embedding from R to itself with that embedding again, I'll get something orientation preserving, because -1 times -1 is 1. And so we see immediately that tau squared is either equal to the identity when C is vect, or at least homotopic to the identity when C is chain complexes. So what's the exercise? And it'll be vague. How does tau interact with the multiplication map? So already, whatever an algebra over all disks, so not necessarily oriented disks is, it has some sort of degree 2 or order 2 isomorphism of the underlying vector space. The question is, how does this play with the algebra? So that's an awesome exercise. And so this theme will not go away. I started out by using oriented, just because we've seen orientations, and that's what I'm going to stick with for now. But there'll be variations of this where you don't have orientations, or you have more structures rather than just an orientation. And those more structures will be quite useful for us. Okay, so let's consider symmetric monoidal functors like this. Finally, what do we get in higher dimensions? Okay, so the empty set, by definition of symmetric monoidal, is going to be sent to the base field K. Not much to that. So again, the objects of this are disjoint unions of R2, oriented, and maps or embeddings that are smooth, respecting orientation. It's not the best definition, but it's the most easy one to digest for now. So R2 is sent to some chain complex, or some vector space, and as before, I'm just going to call it A. Okay. And of course, if I have some disjoint union, by definition of symmetric monoidal, this is going to be sent to some k-fold tensor product. K to be distinguished from blackboard multiply. Okay. So the interesting thing now is going to be what happens on the morphisms. Okay. So here's an awesome trick. Let's again start with what about R2 to R? So whatever the functor is, we're going to get a continuous map. Like so. The question is, how many such maps do we get up to homotopy? Okay, so let's think about what this is. So what's an embedding from R2 to R? Here's R2, here's R2, big one. And maybe my embedding looks something wonky. Okay. Well, let's choose the origin in my domain. I'll call the embedding J. J of 0 gets sent somewhere. It's a well-defined element called J of 0, and I can always just translate it to the origin of my target. Okay. So this is a continuous operation, and as such, let's look at the set of embeddings that send 0 to 0, so that respect the origin. Okay. It's a subspace of all embeddings, and this process actually gives a contraction. Given any arbitrary embedding, I can translate it so that it sends the origin to the origin. So this inclusion is actually an equivalence. It induces an isomorphism on all pi s. Okay. Now let me look at an even simpler kind of embedding. With GL2 of R. Invertible matrices are certainly smooth because they're linear, and they're definitely embeddings. GL2 of R sits inside. And I want to claim to you that this is actually an equivalence, a homotopy equivalence. I'm assuming not everybody has seen this before, so let me explain why. It's kind of a wonky trick. It's just the definition of the derivative. So what I do here, let me write it as though it was a one-variable function. I just take the limit as t goes to 0 of f of x plus tv minus f of x divided by t. So actually, let me not take the limit. There's a homotopy from t equals 1 to t equals 0 called this. So this is a homotopy, so t equals 1, you get the same thing. But well, there's some details to fill in here. But this exhibits a homotopy from an embedding J. That's more or less the trick. Okay. So in fact, there's a contraction from all embeddings into just a collection of invertible matrices. So the space of embeddings is just GL2R. And in particular, whatever this functor f does, so f induces the GL2R action on A. It's a continuous one.
But you forgot about the orientation now? Or?
Oh, sorry. Yeah, you're totally right. Yeah. Determinant positive. Thank you very much. If you didn't demand orientations, you get GL2. Thank you very much. That is an incredibly important point. But now, in TOPS, you might see a further simplification. Inside of here are even nicer matrices called SO2. Okay? So these are the ones where the entries are form an orthonormal basis. And this is also a homotopy equivalence by the Gram-Schmidt process. So yeah, Gram-Schmidt actually shows up. So when you just look at the formulas for the Gram-Schmidt process, you take an arbitrary basis and you make it orthonormal. All the formulas that you write down are continuous in all variables. This actually provides a retraction of all matrices orientation preserving to SO2. Okay, so if we're preparing for next week, you might hear people say, oh, well, there's always a canonical SO2 action. That's where this is coming from. Okay. All right.
Is this particular two-dimensional disk or is it n-dimensional disk?
Yeah. If you take n-dimensional disks, translation still works, derivatives still work. Gram-Schmidt doesn't care how many vectors you've got. So SON is always homotopy equivalent to the space of orientation preserving embeddings of Rn. Okay. So, great. What does multiplication look like? Multiplication comes by looking at the space of all possible embeddings of 2 copies of R2 into R2. And I'm not going to describe this space explicitly, but I want to give you an idea of what this multiplication looks like. So again, let me draw 2 labeled cubes. And my embedding J is going to map them somewhere. Maybe in some wonky way. Who knows? I'm not going to really care about that. And the first thing I want to note, actually, is that oh, okay, everything's oriented. Okay, good. Okay. So this is going to be a connected thing. Whenever you see some sort of configuration of disks like this, I can always isotopy into another. So up to homotopy, there's only going to be one multiplication. But the phenomenon that we're going to see here is that it looks like this multiplication wants to be commutative in some way. Okay, so recall that yesterday we had this swap map given canonically by the symmetric monoidal structure. They just swapped the disk. Okay. And so if I'm to apply the embedding after swapping, I'll get some picture that looks like this. Okay? So a priori, these are 2 different points in the space of embeddings, but evidently there's an isotopy between them. So for now, let me just say there exists an isotopy. The astute among you will notice, maybe because I'm saying it, there's many inequivalent isotopies. I could have moved 2 into 1, or I could have just wound around a little bit and then moved 2 into 1. So the space of ways in which this wants to be commutative is not contractible. It has a pi 1. Okay. So remark. So J is actually isotopic to J precomposed with the swap map. So as a result, whatever this multiplication map is, I'll call f of J. It's a map from A tensor A to A. Is commutative up to homotopy. Okay. And remember, because the space of embeddings is connected, somehow there's only one M up to homotopy as well. However, this choice of M is no longer contractible choice, it's just one multiplication up to homotopy. Okay. So now let me give an exercise. Such facts. Let me do. I keep forgetting to say something. Okay, so now one thing that I haven't elucidated is how does the SO2 action interact with this multiplication? That was the exercise from earlier, and I don't want to discuss that. And for that reason, I'm going to simplify our situation a little bit. So here's actually a simplification. And it requires a structure on manifolds that you might not be used to dealing with, so let me introduce it a little bit carefully. Definition. Let's fix capital X, a smooth n manifold. A framing on X is a choice of trivialization of its tangent bundle. So Tx is a tangent bundle of X, and I choose some trivialization with the trivial value.
If you can.
Exactly, if you can, yes. So not all manifolds admit framings. Of course, not all two. I haven't talked about all two manifolds yet. Okay. Disks do. And so we can set another definition. So disk, n frame, to have objects frame disks. So disjoint unions of frame disks. And so the tricky part is defining what the morphisms are. So a morphism is going to be an embedding.
So we're doing n equals 2 here, or?
Yeah, you can take n equals 2 in that example.
But when you say disk, you allow like an
Oh, sorry, n disks.
Yeah.
Or n-dimensional disks, yes. Thank you, yeah, disk is an ambiguous term in n equals 2. Okay, so C infinity embeddings with a compatibility, equipped with a compatibility. Of framings. So let me just say a word about what I mean by equipped with the compatibility of framings. Because you don't want just maps that have respect to framings. Okay. Well, let me first say why this is a simplification, and then I'll tell you what I mean by respect to framings. Okay, so now let's look at the space of all embeddings between R2 and R2 that happens to respect framings, whatever that means. So respecting framing is going to be some condition on derivatives and then an isotropy between these derivatives in some sense. Okay, I can again use the translation trick to look at embedded framings, framed embeddings that respect the origin. And so now the question is, what happens when I now look at the derivative of this thing? Well, you can imagine that at the origin, I actually have a canonical identification of the tangent space with R2. And this then is going to be the matrix, if it respects that trivialization. It's just going to be the identity matrix in GL2 of R. That is to say, the space of framed embeddings from R into itself is just a point. Okay? So again, the notation 2 is on the board, but this holds for all n. You don't need to apply the Gantt-Schmidt process on the identity matrix. Okay. So in this way, if we now consider functors that are symmetric monoidal not out of orientate disks, but out of frame disks, we get an algebraic structure where somehow A is not equipped with any interesting endomorphism, great, but we still have this interesting space of multiplications. And one of the reasons that this simplifies things is not just because of the removal of this action, so we don't have to think about compatibility. This happens to be an algebraic structure that has been studied before in topology. So definition. In EN algebra, in the symmetric monoidal infinity category C, is a symmetric monoidal functor from framed n disks with respect to disjoint union to C with respect to whatever tensor product you put. And as usual, whatever I assign to Rn, I will call A, and I will just call A the algebra. And you might find me just not writing the F anymore, just because A is somehow notationally what I want you to concentrate on. And so let me just make a remark about the higher dimensional case that is not R2, but say R3, R4, and so forth. So in R2, what we saw was that we'll get some sort of algebra that wants to look commutative up to homotopy. And I made the remark that, how is it homotopic? Well, it's homotopic up to some choice of braiding of these two braids. I don't know if you can see the braids. If I have a movie of these winding around, we can imagine that the time coordinate emerges from the board, in which case this movie depicts a strand of disks. Yeah? Okay. And in fact, I guess pi 1 of the configuration space of 2 points is the braid group on two things. Okay. Anyhow, so there's a pi 1, there's a winding number obstruction to the canonicity of commutativity. If you wanted to repeat this proof in R3, let's say that you chose some isotopy like so. And we saw that if you just do this over and over again, you're going to get some sort of winding number. But actually, in R3, this winding number can be trivialized just by attaching a disk to it. So this movie of disks, if you could imagine a four-dimensional thing, which I cannot, if you threw out this movie in another direction, you can actually cap off that movie with a disk, as drawn in this. Okay, so the pi 1 obstruction vanishes, but your best friend, or worst enemy, could have instead decided to nullify this movie in that way. In this way, the space of commutativity no longer has pi 1, but it has a sphere that is now obstructing. Okay? So as n goes higher, somehow the obstructions become higher and higher dimensional. Okay? So I'm just making a remark. As n goes to infinity, commutativity becomes more and more canonical. Okay. And we obtain something called an E-infinity algebra. And this is the thing that most homotopy theorists will call. This is the homotopy theorists' commutative algebra. Okay, so that's a side remark. You probably won't need it in next week's lectures, except to say that every commutative algebra is an example of an EN algebra. So now let me give you some exercises to give you a feel for what these things look like. Let me make a remark on the framings. Okay, so remark on framings. Okay. So let's fix a smooth manifold capital X. Let's say it's n-dimensional. Okay. So GLN has a classifying space called BGLN. It classifies vector bundles. And so this part, if you can't follow completely, that's totally fine. It won't be super important. So recall that BGLN is just a topological space that classifies vector bundles. Because every manifold has a vector bundle called the tangent bundle. It has a map to BGLN. Okay. Pulling back cohomology classes here is how you get characteristic classes for vector bundles, for instance. What does it mean to trivialize a vector bundle? Well, it means you want to reduce the structure group from GLN to the trivial group. If I have the trivial group called B of a point, because there's a group homomorphism called the inclusion of the identity from the point of GLN, I get an induced map of classifying spaces called B of a point to B of GLN. This, of course, is contractible. Okay, so what does it mean to reduce the structure group to a point? A framing is a continuous map from X to this contractible space, such that Tx is exhibited as this composite.
Is it honestly GLN or is it GLN plus?
Oh, so if X is not oriented,
Okay.
fine. Of course, Y has its own tangent bundle to BGLN. And if Y is framed, Y has its own map to B of a point. And so I've drawn this diagram as though I want it to be commutative. It's some tetrahedron looking thing, but it might not commute. The data that I want, this equipment, is to render this diagram to be a homotopy commutative diagram. So I want homotopies between all these choices of framings. So let me not say too much more about that because I don't know how much intuition that'll give. Now let me give the exercises that I promised to give. exercise.
Space of homotopies is contractible.
What's that?
You said before that, you didn't take into account this choice of homotopy when you argued for Induced raised.
Oh, yeah.
It was contractible.
It is contractible. For Rn, at least. So for Rn certainly. Okay. So, let me get some exercises. Okay. Let's let C equal vector spaces. Let's get back down to Earth. Okay. And show that in En algebra, for n greater than or equal to 2, we did the n greater than or equal to, we did the n equals 1 case yesterday. It's just a commutative algebra. Over K. Let me give another exercise. Let's take C, direct product, sorry, two C tensors, to equal the infinity category of categories with direct product. So again, this is a thing where I only had level 2 and nothing higher, natural isomorphism. Okay. And show in E2 algebra, so we showed what an E1 algebra is if you did the exercise in the last 45 minutes. Anyway, so in E2 algebra is what's called a braided monoidal category. In fact, you can probably see where the braiding comes from. Okay. Now, if you like, I discarded orientations to simplify things. So let's say that you reinsert orientations. So let's say that you look at disk 2 oriented algebras. So these are symmetric monoidal functors F as before, but now we look at oriented disks. I think this is what's called a balanced monoidal category. Is that what you all call it? Balanced monoidal category. I saw the definition at one point in my life. There was some thing. Anyways, balanced. I think that's the term.
You might be more familiar with ribbon, which is...
Oh, ribbon?
No, balance is correct. Ribbon is an extra assumption, but ribbon...
For dualizability?
Yeah, balance plus dualizable is...
Okay, so let me just say that the ribbon category implies the disk 2 oriented algebra. So that's exercise. Anybody have a guess as to what an E3 algebra is? Well, I'll leave it as a question mark with this as a hint. The only obstruction to being honestly commutative comes from spheres. But as you noted earlier, natural isomorphisms don't really have much room for spheres. All right. Definition. Fix in En algebra. In my symmetric monoidal infinity category C. And I know that I've been calling this capital F. Let me just call this A now. I apologize for the abuse of notation. And factorization homologies. Homology with coefficients in A is the left con extension. So again, as before, I'm not going to define what that is, and I'm just going to tell you the computational outcome. So framed-oriented manifold. C tensor. Here's a theorem. Theorem. Fix a framed n manifold, capital X, and a decomposition of X as a union of two submanifolds glued together in such a way that their intersection is just some other manifold times R. So let me just emphasize, so X is n-dimensional, this W is going to be n minus 1 dimensional. Yesterday we saw 2 points times R, for instance. So just to give you a cartoon of what this looks like, so maybe, X is some sort of torus, for instance. A torus can be framed as a Lie group, so that's trivial tangent bundle. And I can write it as the union of, this bit and this bit. And then here, the overlap is S1 times R. Okay, that's an example. Now, I want to note again that whatever factorization of homology assigns to S1 times R, this is an algebra. Okay, so here, so now, note, whatever I assign to W times R in factorization homology is an E1 algebra. It's what I called an associative algebra or an A infinity algebra yesterday. But hopefully you understand what I mean by E1. En for n equals 1. Oh, no, I should say one thing. For one manifold, the framing is the same thing as an orientation. Once you orient to one manifold, you've framed its tangent bundle. It's trivial because it's one-dimensional. So that's why I can write E1 algebra. Here is the same thing as an associative algebra. And why is that? Well, again, if I have W times R and 2 copies thereof, I can just embed it into a single copy of W times R. It's the exact same proof as yesterday. I just crossed by W. Okay. And likewise, these xi times R, or these xi's, are modules. They're modules again because I can take this cylinder. So I can take this left half of the torus, I can squeeze it into itself because it's collared, and then I can shove a copy of the cylinder right here. Okay, so this gives an embedding of left half union cylinder into left half. A tensor M into M. Okay. So given such a decomposition, we naturally observe that we have an algebra and 2 modules, just as yesterday. And the excision theorem, tensor excision, is that the factorization homology of the big manifold with coefficients in A is equivalent to the factorization homology of A with respect to the 2 ends tensor together, but over the common algebra that acts on this. So in practice, this is the way that you're supposed to compute things, even though in most algebraic examples I've tried, it's been way too hard. I think when you have a little bit more structure, then you can actually compute these things in practice. Okay. Well, as done by several people in this room, actually. Okay. That's just the definition. I guess it's important now to try to see some examples and some upshots. So here's an unenlightening example. Let's fixate 2 algebra. We'll call capital A. So this is just some 2-dimensional disk algebra. And what's factorization homology of a torus with a particular framing? The torus admits many different framings. But I'm going to ignore which framing I take for just a moment. So I can now decompose the torus in the way that you might expect. So again, it's just some 2-dimensional version of the horseshoe, or macaroni if you like, and the intersection is just 2 cylinders, as indicated here. Okay, so this is the factorization homology of left macaroni A, right macaroni A, tensored over, I don't know, 10A, A. Okay, great. Which, so So you'll now recall that this is circle times the real line. Union S1 times R of A. And so now all we need to do is compute what is the factorization homology of A over S1 times R. Give me 1 second. But given S1 times R, I can just take the same decomposition from yesterday, just direct product it with the real line. So now I have these horseshoes and this co-horseshoe. And so the upshot is this can be identified with a particular, let me write it here. So now it's just factorization homology of A with R2, respect to R2 disjoint union R2 A, R2A. So I've written the cylinder as a union of two R2s, and the intersection is two strips. Okay. And so this I will just call Hochschild chains, a version of Hochschild chains. So this is some weird thing where, the left and the right hand side are already these Hochschild chains of A. Things that looks like, Durand differentials when A was commutative. And the weird thing is because we're in a higher dimension, I think Dredd called this.
So what was this last step?
This one?
Why do we have this again? I'm kind of maybe it's obvious.
So this is like A tensor A up. So R2 disjoint union R2. Disjoint unions are sent to tensor products. So the factorization homology of a disjoint union is just the underlying functor F. So I get A tensor A as vector spaces. And the claim is, how are you multiplying things? Well, again, you have in these directions. Now, of course, in the E2 case, let me just write it A tensor A. Okay. So the point is, now because we're in higher dimensions, this is a phenomenon that I think Dredd called stacking yesterday. This circle value, so we saw that Hochschild chains was associated with a circle before, but now by taking the direct product of the circle with R and thinking of it as a two manifold, the circle inherits its own multiplication. So Hochschild homology now has a multiplication, and this is Hochschild homology of Hochschild homology. This is Hochschild chains of Hochschild chains. Okay. And now the important thing here is before there was a circle action on this doohickey, and now this has framing preserving diffeomorphism action of T2. And in particular, for the Lie group framing, it has what? A GL2Z action. So let me just make one more remark. Got 3 minutes to remark. Let's suppose that the infinity category that I take is the category of categories with direct product, and it's fixed in E2 algebra. Call it R. R for rep UQG, for instance. So in E2 algebra, recall from the exercise, it's just a braided monoidal category. Okay? And so let me assume that it's ribbon or something, so we actually get oriented manifolds. So let's say a disk2 oriented algebra. Okay, so for example, a ribbon category gives rise to such a thing. The reason that I changed the algebras that I want to consider is there aren't very many frames to manifolds. For instance, closed surfaces of genus G, their tangent bundle is non-trivial, so they won't admit a framing. And I wanted other kinds of Riemann surfaces to show up. Okay. Then so if we have factorization homology here with coefficients in R, this is a functor from two-dimensional oriented manifolds into categories. Okay. And in particular, some Riemann surface of genus G with an orientation is going to be sent to some category. Okay, so this is a category. thing that I haven't mentioned yet is that every manifold actually has a favorite manifold that maps into it, called the empty manifold. And so recall, what does symmetric monoidal mean? It means that the empty set is sent to the unit on the right-hand side. Okay. So now, if my category is a category of categories, the unit is just the trivial category with one object and only the identity morphism. The empty set is going to be sent to the trivial category. And this canonical embedding of the empty set into sigma g is going to give a functor from the trivial category to that category. A functor from the trivial category to a category isn't much data, it's just an object. But it's an important object that I think you might see sometime next week. The point being, factorization homology, the output isn't just an object, it's always an object with a pointing. So for instance, a category with a chosen object. And finally, let me just say one last thing. We have an induced continuous map from orientation preserving diffeomorphisms of sigma g to functors from this category to itself. Okay, so remember this is a space where the vertices were functors and the edges were natural isomorphisms. Okay. So in particular, by continuity, this actually induces a map on pi naught. And of course, because we have a functor, anything invertible is sent to anything invertible. So this actually gives you up to natural isomorphism, some non-trivial auto functor of this category, and in particular, an action of the mapping class group, the homotopy, on this target category. And my understanding is that in representation theory, there were certain categorical invariants, or certain things that, by hand you could construct a mapping class group action, and maybe it was like pretty hard to do that. But if you can exhibit such invariance as arising from factorization homology for free, you get an action of the mapping class group. Okay, so tomorrow, Thursday, I'll talk about TFTs. I'm done for now. Thank you.
Any questions?
Maybe I can comment. I'm not sure if you were going to cover this, but I think the computation there might be a nice place to highlight this Fubini formula.
Yeah, that's true. Yeah. Y'all remember Fubini from calculus? So if I have a direct product of manifolds, let's say x1 times x2, possibly of different dimensions, if I take their factorization homology, so whatever dimension x2 is, I can cross it with R of some Euclidean space, so R to some dimension, I get a factorization homology. And some might call this, just ignoring the Rn, factorization homology of A with respect to this. The reason is because when I use factorization homology, compute factorization homology of A with respect to x2, you're only using the multiplications in the x2 direction. So even though A is an n-dimensional thing, it has n-dimensional multiplication, let me only use those coming from the dimension of x2. Okay, so I can forget an En algebra to an Ek algebra, where K is the dimension of x2. Okay. But this now has a remaining dimension of x1 component. So this is itself an algebra, an E dim x1 algebra. Now I can take that over x1. Is this what you mean by Fubini?
Yeah.
So yeah, it's, and of course, this is symmetric in x1 and x2, so you could have done it the other way. And it's called Fubini because that's how you integrate in differential calculus.
And I think now in your computation it's even clearer that we're taking Hopfield homology of Hopfield homology.
Yes.
The circle correct.
Totally. Thank you.
So actually, just about this point. So yesterday we saw that integral over S1 A was just A modulo commutators.
Yes, for vector spaces. Yes.
Yeah. So that was the easiest non-trivial example where something happened.
Yeah, totally.
And so, what would be the analogous statement
Yeah,
you know, for integral over T2.
absolutely. So the analogous
A.
statement for a commutative. Okay, so in vector spaces, there's an exercise that says any E2 algebra is actually a commutative algebra. Because vector spaces doesn't have enough room to see the braiding. So
Yeah,
any-
that's why I'm asking for an interesting example.
yeah,
Because
so
the easiest non-trivial answer will actually see something there.
I'm assuming actually, like maybe David's the person to ask using braided monoidal categories. There you don't need all the higher homotopies of chain complexes. If you want a simpler example, I shouldn't waste everybody's time trying to think about it here because it won't be quick enough.
It's a braided monoidal category. If you take an integral over a circle, then you get class functions. So you get, G-equivariant, so G-graded vector spaces essentially. You get class functions, and then if you take a circle if you take another integral one more time, then you get the partial homology of the class function.
Depends what you mean by class functions, because class functions are already commutative.
But I don't mean
Exactly.
multiplication, I mean with
Exactly.
convolution structure.
The thing that makes it associative. Yeah.
So you said that for these two framed algebra categories is going to be braided monoidal.
Braided monoidal category, yeah.
So what happens for these cohort? Like is
Yeah, there's a word called balance that apparently is like,
so
yeah, I don't know.
Balanced, and that's it.
Exactly. And ribbon categories are apparently examples of balanced categories. I must admit I'm just regurgitating words because I've never worked with those.
Okay, and I was thank Hiro again.